What's up guys, this is Massey, welcome to another video. In this video I want to talk about reaction rates. And this is the first part of chemical kinetics. What is chemical kinetics? The area of chemistry that concerns reaction rates is called chemical kinetics. So we are dealing with rate of reaction. Rate means speed. And we will see the concept in details later on. For example, let's consider this reaction. It says, consider the decomposition of NO2. We have this balanced reaction, 2NO2 gives 2NO plus O2. And then you can see the reactants on the left hand side and you have the products on the right hand side. The concentration of reactant, which is NO2, is decreasing over time, and the concentration of products, which is NO and also oxygen, is increasing over time. So it means that the reactants are consuming over time and the products are forming or producing over time. So the concentration of NO2 is decreasing over time and the concentration of NO and O2 is increasing over time. So chemical kinetics deals with the speed or rate at which these changes occur. So the speed of reaction or rate of reaction is really related to the speed that these concentrations are changing. Sometimes you are dealing with concentration of reactants, sometimes you are dealing with concentration of products. The speed or the rate of a process is defined as the change in a given quantity over a specific period of time. So in this case, when we are dealing with reaction rate, it's mostly we are dealing with change in concentration or change in molar concentration over time. For chemical reactions, the quantity that changes is the amount or concentration of a reactant or product. Reaction rate of a chemical reaction is defined as the change in concentration of reactant or product per unit time. So let's see it in terms of formulation here. Rate of reaction equals to concentration of A at time T2. It means that final concentration of A minus concentration of A at T1 or initial concentration of A divided by T2 minus T1, which is delta T, change in time. So if we summarize it, it's going to be rate equals to change in A, or change in concentration of A, divided by change in time. Delta T, that's called delta. Delta T is change in time. And delta concentration of A is change in concentration. And if we put it in bracket, it means that we are dealing with molar concentration. So whenever we are dealing with molar concentration, it means that we are dealing with this, we need to put this bracket there. So change in molar concentration, the molar concentration is mole per liter. That's the unit for molar concentration, mole per liter, which is number of moles of solute dissolved in the volume of solution per time. This time can be minutes, can be hours, can be second. Let's say if it's in terms of minutes, we have mole per liter per minute, or mole per liter per second, or mole per liter per hour. We can have any of these. Mole per liter per minute is the most common one out of all these examples. So this change, it means that the change in concentration sometimes is positive and sometimes it is negative. Why we say that? Because as we saw in the previous paper, sometimes the concentration is decreasing, sometimes the concentration are increasing. If you are dealing with reactant, the concentration is decreasing over time, and if you are dealing with the product, the concentration is going up. So this rate or this delta C over delta T is gonna be sometimes positive, sometimes negative. If we are talking about the reactant, it is gonna be negative. If we are talking about the product, it is positive. So if we put a negative sign behind this fraction when we are dealing with a reactant, it means that the rate of reaction by agreement is going to be positive all the time. So although this ratio is sometimes positive, sometimes negative, but for reactants we put negative behind it to make it positive. So for convenience, we will always define the rate as a positive quantity. The rate is not constant, and the rate of reaction is changing with time. So at different times we have different rate of reaction. The value of rate of reaction at a particular time is called instantaneous rate. So let's see in this example. For the decomposition of NO2, we had it in the previous page. 2NO2 gives us 2NO and O2. We have rate of reaction of NO2, rate of reaction of NO, and rate of reaction of oxygen. Rate of reaction of NO2 means the change in concentration of NO2 over time, change of concentration of NO over time, and change of concentration of oxygen over time. But it's gonna be the relationship between all these three rates is really dependent on the coefficient we have it behind all these chemicals. And as I said earlier, when we are dealing with the reactant, we need to have a negative sign before the fraction to make all positive. So we find out the relationship between the rates of reaction of all these three equipments is going to be like that. We're going to say negative R of NO2 divided by 2 equals to R of NO divided by 2 equals to R of O2. So we divided by the coefficient, and this one the coefficient is 1, so we just put 1 in the denominator, which you don't see anything. So it means that the rate of reaction of NO2 equals to rate of reaction of NO, and it is double than the rate of reaction of O2. It means that the change in concentration of NO2 is twice as faster as the change in concentration of oxygen, or change in concentration of NO is exactly has the same rate than change in concentration of NO2. So I can put it this way. So when we are dealing with A plus B gives us CFC and DFT. I put the coefficient in lowercase, and uppercase are the compounds. A and B are the reactants. C and D are the products. So we can find a relationship between these rates. We can say negative RA divided by A equals to negative RB divided by B, lowercase b, equals to rate of reaction of C divided by C equals to rate of reaction of D divided by D. That's how we find out the relationship between the rate of reaction or rate of change in concentration of each of these compounds in a balanced reaction. You need to make sure that you balance these reactions before you write the relationship between the reaction rates. And I mentioned that earlier, the rate of reaction is changing with time and it's not constant. So usually the rate of reaction for reactants is going to be high in the beginning when we have higher concentration of reactant, and it is going down over time until we reach a plateau. On the other hand, for products, initially, most of the time in these reactions, we have 0 of our products, and over time is increasing until all reactants are used up or we reach to an equilibrium. So that's how the reaction rate of reactants and products are changing over time. Okay, let's see some examples now. The first example, it says, consider the reaction 4pH3 in gaseous phase gives us P4 gaseous phase plus 6H2. If in a certain experiment over a specific time period, 0.0048 mole of pH3 is consumed in a 2-liter container each second of reaction, what are the rates of production of P4 and H2 in this experiment? So first of all, we need to find out if it's balanced. Yeah, we have 4 phosphorus and we have 12 in both sides. That's good. It says in a certain experiment over the specific time period, 0.0048 moles of pH3 is consumed in a 2-liter container each second. So it means that the change in concentration of pH3 over time is 0 minus 0.0048 divided by 1 second. That's mole per liter. And 0 minus 0.0048. Why 0? Because that's going to be the second concentration. It means that the difference between each second in terms of concentration. So as I said, since it's consuming and it's the reactant, we need to put the negative in here. So negative in here, that's going to make it positive. And the reaction rate is going to be 0.0048 mole per, actually it says 2 liters, so we need to divide it by 2. So that's going to be 0.0024 mole per liter per second. Or if you want to show it in terms of scientific form, it's going to be 2.4 times 10 to the power of negative 3 mole per liter per second. Or you can write it this way, 2.4 times 10 to the power of negative 3 mole liter to the power of negative 1 s to the power of negative 1. So it says what are the rates of production of P4 and H2. So based on the relationship here we have in the reaction rates, we can say negative R of pH3 divided by 4 equals to R P4, that's going to be positive because that's the product, divided by 1 equals to R H2 divided by 6. It means that RP4 equals to negative RPH3 divided by 4. So it means that we need to divide this one by 4. So that's going to be 2.4 times 10 to the power of negative 3 divided by 4. And that's going to make it as 6 times 10 to the power of negative 4 mole per liter per second. On the other hand, we have reaction rate of hydrogen, which in that case is going to be 6 over 4 times RPH, which is going to be 6 over 4 of 2.4 times 10 to the power of negative 3. That's going to be 3.6 times 10 to the power of negative 3 mole per liter per second. So that's the rate of reaction of hydrogen and P4. Let's see another example. In the Haber process for the production of ammonia, we have this reaction, N2 plus 3H2 gives 2NH3, all in gaseous phase. What is the relationship between rate of production of ammonia and the rate of consumption of hydrogen? Rate of production of ammonia and rate of consumption of hydrogen. So again, that's related to basically the coefficients. It is balanced, so we can say negative Rn2 divided by 1 equals to negative R of H2 divided by 3, because these are the production, and they have negative sign because they are in reactant side, and it has to be equal to reaction rate of ammonia divided by 2. And if you want to find out the relationship, you can say RH2 equals to 3 over 2 of negative RH. Or you can say change in concentration of H2 over time equals to 3 over 2 times change in concentration of NH3 per change in time. So basically that's going to be the relationship between the reaction rate of consumption of hydrogen and reaction rate of production of ammonia. Now in this example it says at 40 degrees H2O2, which is the hydrogen peroxide, will decompose according to the following reaction. So 2 hydrogen peroxide in aqueous phase is going to be decomposed to 2 molecules of H2O in liquid phase plus O2. The following data were collected for the concentration of H2O2 at various times. So at 3 different times we have 3 different concentration of H2O2, and as you see here over time the concentration of H2O2 is reducing, and that makes sense because H2O2 in this reaction is a reactant. And the units are given, time is in terms of seconds, and the concentration here is in terms of mole per liter. Part A says calculate the average rate of decomposition of H2O2 between 0 and 2.16 times 10 to the power positive 4, which means that the difference between these two, and use the rate to calculate the average rate of production of O2 over the same time period. And part B, it says what are these rates for the time period 2.16 times 10 to the power 4 seconds to 4.32 times 10 to the power 4 seconds. Let's start with the part A. So what I can do, I can say that changing concentration of H2O2 negative over time divided by 2 has to be equal to changing concentration of H2O over time and changing concentration of O2 divided by 1. It means that the rate of reaction of O2 equals to negative rate of reaction of H2O2 divided by 2 with 2 different signs. So what we can do here, we can say the rate of change of H2O2 from 0 to 2.16, I can say R of H2O2 will be 2.16 times 10 to the power of negative 4 minus 0. That's going to be the denominator, and concentration is changing from 1 to half. So we need to write the initial one here and the final one in here, and then we need to multiply it by negative sign. So that's going to be positive 0.5, 2.16 times 10 to the power 4. Then the answer is going to be 2.31 times 10 to the power of negative 5 mole per liter per second. That's the rate of change in H2O2. And then if you want to find out RO2, that's going to be 1 over 2 of 2.31 times 10 to the power of negative 5, which will be 1.16 times 10 to the power of negative 5 mole per liter per second. That's the answer to part A. Part B, it says find it for the other time interval. So we can say R of H2O2 is going to be negative 0.25 minus 0.5 over 4.32 times 10 to the power 4 minus 2.16 times 10 to the power 4. That will make it as 1.16 times 10 to the power of negative 5 mole per liter per second. And rate of change in oxygen is going to be half of that, which is going to be 5.8 times 10 to the power of negative 6 mole per liter per second. So that's going to be the rate of reaction of oxygen. So now let's see the last example in this video. It says consider the general reaction A of A plus B of B gives us C of C. And the following average rate data over time period is rate of reaction of A over time is going to be 0.008 mole per liter per second. Change in B over time is going to be 0.012 mole per liter per second, and change in C over time is going to be 0.016 mole per liter per second. Determine the set of possible coefficients to balance this general reaction. So as you see here, if we divide this one by this, so 0.012 divided by 0.008, when you divide it, it's going to be 1.2. It means that rate of change of B is 1.5 faster than A. So the relationship between coefficients is going to be 3 and 2. What about this one and this one then? I'm going to say rate of change of C is 2 times faster than the A. So C is twice as fast as the A. So we can say we have negative RA over A, negative RB over B, and RC over C. So you can say RC equals to negative RA times C over A. It means that C over A is 2. On the other hand, for RB, if you write it the same way, is going to be RA times B over A, which we know B over A is 3 over 2. So we can say A is 2, B is 3, and C is 4. So the reaction is 2A plus 3B gives us 4C. So that's going to be the balanced reaction in this example. I hope you enjoyed this video. Please leave me a comment if you have any question. Please don't forget to subscribe to this channel. You can have access to many other videos regarding chemistry, physics, and math. Thank you for watching and have a great day.